My technician, you're hired. The pay is low, but the rewards are really high.
It is nothing.
So, yeah. So, all right, so this theoretically is running. Mike's on that too, so hopefully Mike can hear.
Yep.
All right, good. All right, I can hear you too. All right, so just interrupt if anything goes wrong with this. Let me see. Did this? Yeah, this opened, and this is slides 3. This is, I don't know if this is the updated. Did I download the updated one? I updated both of these things. Sorry. Oh, I just did it, right? So that should have been the uploaded one. Wow, that's weird. All right, so anyway, I guess this is the upload one. Pretty functional today. 2C is the right thing. So, all right, so the recording of the homework thing, do I need to go through that again, or is it? Have anybody looked at the homework? And do you need help with it, or? I should kind of go through it a little bit. Because the recording is going to be totally useless. How about I just go through the questions on this? One group already turned it in, so.
That's the last one.
Oh. 7, right? This. Yeah. Yeah. So this they're using this Tanaka model. So they have the penny
Hey,
pan.
Dr. Beaucage,
Yeah.
just as a heads up for viewing online, you're not sharing your screen. At least what I'm seeing is like an overhead camera of you and like sort of I see both screens, but it's like a camera on the ceiling.
I think it's supposed to show you. Oh, I know. No, I know what the problem is. All right, I have to hit this.
Yeah, that's better.
Sorry. Yeah. There's the controller. You have to send it to the web. But it was already set up for in here, so no one noticed. Right. So anyway, he's got penny PAM, which is kind of like a protein amide side group on a polyethylene, basically a vinyl. Right. So it's got this kind of hydrogen bond. So it's got water will hydrogen bond with it. It sticks. Methanol can also hydrogen bond with it, so it sticks. And Tanaka said that these happened. Well, the energy of that sticking is going to be different for the two. And apparently it's cooperative. In other words, if you have one water, a methanol won't fit. Otherwise, you just get, I mean, there's another option here. You just have a mixture of things all over it. I mean, the reason why Tanaka likes this option is he already had a theory for helice formation, first order transition going from a coil to a helix, right? Like it would have a heat of formation. It's a first order, right? So anyway, so he already had that theory written up, and it would go like, and in that case, you would have like tactic polypropylene, then non-tactic, or some kind of defect like branches that couldn't form a helix. So it would have regions where it would have to be like this. And this later, you could think that this later led to the blob model of coil collapse. So it starts out logical, and then it gets added, and because the math is there, then you have a hammer and everything looks like a nail. So then you just use that model and keep going with it, right? There's advantages and pitfalls to that approach. It's pretty common in science, right? So anyway, this is the thing. He's got the helical model, so he just says, well, the water is kind of cooperative. So if one water comes in, another water, one methanol, another methanol, so you get these regions, right? And then in between the regions, you're going to get this blob forming. And then because the blob has kind of more entropy than the helix or than the bonded, and there's an energy involved, so he has an entropy involved in the randomness, and he's got well, the randomness is really like these helical things make a walk that's like a random walk, which these are actually bonded water and bonded methanol, but I think it's kind of helices in the theory. So that has an entropy that reduces the longer the length of the helix. So you lose an entropic, but you're gaining enthalpic because these bonds release energy when they bond. So you lower the free energy by bonding it. And that's, if the temperature goes up, that benefit depletes because the things want to fly off. Right, so it's a competition between this entropy number, which is just how many of these things, counting it up like a Boltzmann. So you take the log of the number, gives you the entropy. So the more the number, the higher the entropy. And this enthalpy, which is this bonding of the things to it. Right, so it's compete against each other. They find a critical temperature. So you have like delta G is delta H minus T delta S. If delta G is 0, then you have this critical temperatures delta H over delta S. It's like the melting point would be the enthalpy of melting divided by the entropy of melting. Gives you the equilibrium melting point. Right? And here, entropy would be like this squiggliness of this thing, and enthalpy is the bonding energy of the thing. Right? So you can get a first order transition out of some model like this. It's possible. Anyways, that's his model. He ends up with an equation for the enthalpy of the system, which is just like how long is this thing times some number, how long is the methanol thing times some number, add those two together. The sum number ends up, it's an entire addition to the paper, a supplemental that's not published with it because it's too confusing. And he can get that number somehow. It's basically magic. Like we can't figure it out. It's not really possible without spending a PhD, maybe 2 PhDs figuring out what Tanaka did. And the Russians, I don't think they necessarily really understand it either. They just took his equations and plugged the numbers in. And they got that theta, which is the enthalpy for this strand. And then they add the two and they get the enthalpy for the whole thing. And so, and then the entropy is like how many of those, so it's NL squared kind of entropy. Same as the polymer chain. Anyway, so with that, you can get a first order transition. If the energies of these two are different than each other, then you can get this kind of behavior from Tanaka's theory. This kind of thing, like you can get a coil collapse. So first order coil collapse and a first order coil expansion going up in composition of methanol. Just kind of interesting. So it's like a miscibility window, a miscibility gap in the methanol concentration. So you have pure methanol, it's soluble, pure water, it's soluble, and you find somewhere in between, it's insoluble. So, I mean, you could think that could be used somewhere for something, hard to tell, but that's the idea of the paper. And then he uses this DSC. So I went through a little bit what a DSC is and what a DTA are. So I don't know if it's not really a lecture. I'm wondering like how much you need, like you're going to run across like any number of instruments like in your career, and every one you're going to have to pick up and figure out what's going on. And the best thing to do is to say, I want to build this instrument. And what do I need to build it? Then what am I going to do with it? And it's going to spit out some numbers. And what am I going to do? Like take those numbers to get what I want. Like you build an instrument because you want something, or you want the enthalpy of whatever's going on with this thing. And it's a small number. So what do you need to do that? Well, you're going to have heat it. So you need a heating coil or something, right? And then you're going to have to measure the temperatures. You have to throw the thing together. You can have a controller computer with it. On that level, you should be able to design it. This is a historic thing in science. Okay, like in the original science, which is like 1850, in order to get a PhD, you had to build a machine. Really, like that's really what they required. So you had to build some kind of machine, and nobody bought any machines. That would be seen as like cheating. So basically, there's roots in this that go back a long way that you should be able to build the machine you're using. That way you can kind of understand what's going on with it. So that's the logic behind this. It kind of works. Like if you can buy so many machines now and they're complicated that you can have no idea what you're doing and what the pitfalls are. And then, so if you don't know how to build it and you don't know kind of how to reduce the data from the raw measurement or what the raw measurement is, it's one of the pitfalls of science. So generally people want to see you build the machine on paper, like how to build it. So that's the idea. Any question about a machine like a DSC, it boils down to how do you build it? You know, how do you actually, what components do you need? How would you put it together? Then what do you do with the data? Then what are the pitfalls with doing that measurement? I mean, here, if you use a DSC, the pitfall is the computer, every time you add a component to it, there's going to be an error involved in it. And here, if you're measuring such a small number in a microcalorimetry, adding the computer feedback loop is going to make it so you can't measure it. So you want to really have a DTA where it's a direct measurement of the temperature, which is the simplest thing you can do. So you put a resistive thermocouple in. It's just that you have two metals together, and the electrons in the metal, when it's hot, move more, right? And when it's cold, they move less. So this is called thermophoresis if it's in a gas. Like the electrons or the atoms will go to the cold part and they'll stick there. So you can have like electrophoretic, thermophoretic deposition. Like in a tailpipe of a car, it's all black on the inside because the pipe's cold, the gases are hot, the carbon soot wants to collect on the cold part because it moves less there. So statistically, it collects there. Same with a piece of metal in the hot part, the electrons are moving, in the cold part they aren't, so they tend to pile up in the cold part. So you get a voltage. And in different metals, this difference is different. So like the electron motion due to temperature is different in different metals. You hook to, that's called a Seebeck coefficient, is like how much temperature affects the motion of the electrons in the, so you put two metals together, then the electrons can flow through. Basically, you get a voltage drop if you have a temperature differential between the ends of the two, and you can measure the voltage at the cold end and see what the temperature was at the hot end. That hope that kind of makes sense. It's related to thermophoretic deposition. It's the same process. It's just for electrons make kind of a gas in a metal, so they can fly to the cold part. So that's what you use basically to. That's one kind of thermocouple you can use. That's a what's that called? Metal die something. The other one is resistive, so you just run a current through it, and the resistance changes with the temperature. The resistive is more sensitive than the coupled metal one, thermocouple. But anyway, so you have some kind of thermocouple to measure the temperature of the two. You have a heater, blah blah blah. Right. So you can kind of, I think you can kind of Google that and get a better description of it than what I can give you. You can go to the thermal analysis, the companies that make these, and they can tell you in detail, like every component of the machine. Anyway, I think you better get used to, like, you walk in, you have to run a FT Raman microscope. You know? So you're going to stick your thing in there, and then what's going on? Like, so you have to be able to figure it out on your own. People telling you every instrument and how it works isn't exactly the best approach to it. So somehow you have to be flexible enough that you can take what you know about and logic and kind of put together how those machines work. So that's the point of this thing. And the point of any question about a machine is how do you build it, you know, really. So start out like the construction of it. Then co-expansion factor we talked about, that's R squared over R squared, the expanded coil versus the unexpanded, and expansion factor. So it gets smaller when when you have a collapse. So it goes less than 1. First order and second order, that's also like a major topic. You have to be able to define first order and second order. So first order has a heat, has a volume change, has an entropy change. There's a delta, so there's a discrete change in it. So it's like a clip of the thing, like this, boom, the volume change. This is plotting, yes, this is the volume, the expansion factor, and it discretely changes. So the enthalpy, that means there's also an enthalpy that changes. And there's also an entropy that changes. Right? So if it's not first order, you'll get a change in the slope. So the thermal expansion coefficient would be like the change in this with respect to temperature with respect to mole fraction methanol. So that coefficient would change. Like the first derivative would have a discrete change. You'd have a change in the slope of the heat capacity with temperature, and that change in slope would be discrete. It's a step. So the second derivative would be like a discrete step versus the first derivative is a discrete step. The actual heat capacity jumps. So anyway, so first order and second order have to do with the derivatives. And typically first order is like a melting, and second order is a glass transition. Those are like the normal ones. But you can have like a Curie transition in a metal or in a magnet. So you have like the magnetic fields all aligned. This is where first order and second order were first invented, was in magnets. Everything goes back to magnets for some reason. So you have magnetic moments, they're all aligned. And then if you reach the Curie temperature, they become unaligned. That's a first order transition, there's an enthalpy involved in it. And there's no volume change, I don't think, but there's definitely delta H and a delta S. So that's the Curie transitions, like the first order transition, the standard one that's modeled from all the others. So anyway, so LCST, that's like the signs of it. You have chi equals B over T. In order to get LCST, you have to have A plus B over T, and the signs of them let you get the LCST. You have to figure out what signs you need to get that. Kind of how these special structures can influence. This is just take a look at those papers and figure out how water organizes. And then RG by RH. So if you have a sphere, RH is R and RG is square root of 5/3 R. So square root of 5/3 is bigger than 1. So this thing ends up being 0.77, I think. And then if you have a coil, though, because the RG is like taking the whole coil and saying, if I find the center mass, and then where would I put the mass if I spun it around and have the same moment for like a wheel? That turns out to be smaller than what the drag coefficient of that whole big blob thing is, or big coil thing, right? Because the coil thing's got like solvent entrained in it. So the whole monster is moving around, and RG is just the structure. It's like case RH by RG gets larger than 1.2 or something. So, and it depends on how much the solvent drains or doesn't drain. So that's the Zim model, is it doesn't drain, and the Rouse model is it totally drains. There's two models for the drag coefficient. So this ratio can change depending on what model. But basically, this thing will be larger than 1 if you have a fixed coil, if you have not a 3D structure. So bigger than 1 or less than 1 is kind of a deciding factor. If it's 3D or some kind of fractal structure, like a branched whatever, dendrimer or anything, it's going to be bigger than 1. That's kind of the rule of thumb. There's some actual values, but rule of thumb is 1 is the cutoff. We'll talk more about RH like in a little bit. And then hydrophobic effect. I mentioned that there's a couple things. It's just like look at those things. This Shurega, I guess he's from Cornell, like National Academy of Sciences. He did stuff on how you get RH for proteins. And then he did some stuff on this, how water structures. And he wrote this paper that's like my life story or something. 60 pages, I guess, did his life. So that's kind of everything he did is in that 60 pages. So he goes through the stuff. It's kind of interesting to flip through. And then there's also a book in there on clay thrates and things that has to do with water, how water organizes around organics, and how that can be important to the end of the earth, kind of. This methane clethates that are at the bottom of the Arctic Ocean, and also in Siberia. And then it also could be used for hydrogen storage. So clethates, they're important to know about. You probably see it in the newspaper at some point. You know. It's not particularly science, it's kind of more popular topic. Anyway, hopefully that's okay for that. That's it. I guess, unless there's questions. You can email me if you have questions on it or something. Identified a potential security concern. Let's see. Slide masters. I think, is this the right set of slides I need? I'm way down at the bottom. I don't need that. 2C is the one I'm in. Right? Through this business. Maybe we did. Figure out where I am. We're way beyond that. Are we done with this one? No, we haven't done second half yet. So, but we'll be. This is past too far. I was at like RG. Didn't mess this thing up. Yeah. All right. This is where I want to be. All right. So, sorry. Actually, I'm way back here somewhere. Right. So hopefully this is the new version of this thing. All right. So, all right. Here, this is where I want to be around this. Okay. So I just showed last time, like you can do Grenet's law. That gives you this knee. If you do log I, log Q, it gives you this knee. And then the way that's plotted sometimes, they call it a Grenet plot. So they take log I by the I naught here, which I naught would be the plateau part of this. So you normalize that by the plateau. So it goes to 1. Take log of that. Log exponential gives you the argument. Then you get a slope and you plot against Q squared. So you get the slope is a negative slope and it's RG squared over 3. That's called a Grenet plot. The problem with that, I should probably demonstrate that, but if you take any point in this curve for polymer chains, this is power -2, that's the Grenet part, which would be the coil. If I take a small enough range in here, I can put a Grenet plot and get an RG for it, and there is no RG there, right? So basically, it's like saying, well, I have this kind of knee-shaped thing. If I take the flat part of that knee thing, it almost looks like a straight line, and it can fit any part of the curve. So unless you know what the RG is, then you can't really use a Grenet plot to get the RG. So it's a little bit of a catch-22. That's a pretty good book to read, Catch-22. It's about World War II. The catch-22 is that if you're crazy, you can get out of the army. But if you're in a war, you're naturally crazy, so you can't get out of the army. So the guy's keeps putting in papers to say like he's crazy, he needs to get out of the army because he thinks people are trying to kill him, and he's in a war. You know, the people are trying to kill him. It's kind of a funny book. Anyway, oh, and the town they're bombing in that book is a town where Lyondell, that Mike works for, that's their main plant is in that town. You know, it's in Italy, but so they go on bombing runs to that town. But anyway, so then that's one transition of this thing. The other way, exponential, you can expand to 1 plus the argument, and then plus 1 over 2 factorial times the argument squared, and then plus 1 over 3 factorial times the argument cubed, etc. And if it's negative, it goes plus minus, plus minus, plus minus, right? So if you take just usually people just take the first 2 unless they have a reason to take the third. So as long as R, G, and Q are small, like less than 1, so that's the case if Grenet's law is working, because you can see if they get larger, it doesn't work. Like the red dashed line doesn't fit it. So then you can expand this, use this exponential expansion to get 1 plus the argument. If you take 1 over I, then this becomes plus. So that becomes plus. So that's kind of the basis for the Zim plot. That's one of the steps of it. So Zim plot is going to be 1 over I, or some like a reduced I, 1 over R, Rayleigh ratio, and then versus Q squared, which is sine squared. Q is 4 pi over lambda sine theta, sine of the angle. So it's going to be sine of the angle squared. So you're going to have 1 over I versus sine of the angle squared would be like the Zim plot to get, and you're trying to get partly RG. So from the slope of it, you're going to get RG in the limit, kind of in the, well, and then you also trying to get the prefactor of this. We'll talk about like in a little bit. Like the prefactor gives you the chi parameter and this, so you can get RG and the chi parameter if you do a concentration series and you do an angle series of light scattering. So that's kind of the Zim thing. So usually I go through a little bit about kind of scattering, so this is like the best thing. See, you're coming in with a radiation, right? And it's got a wavelength. So you have, say this is actually 2 times the wave, or half the wavelength, I guess, between these. So it's like this is like the amplitude squared. So you have, so let's see. All right, so the intensity that you measure, so there's an electromagnetic wave. Right, so I'm plotting the electric field part of it. Right, and it's got a wavelength. And if you take Maxwell's law, says you have like the electric field part going with your fingers, and your thumb goes with the magnetic field. So anytime you have an electric field, there's a magnetic field with it, if it's changing. So if the electric field is changing, then you form a magnetic field. If magnetic field's changing, then you have an electric field. That's a doorbell rule, right? So you have coil of wire with the current in it. So the electric field's going around in a circle, and then you have a magnet in the middle of it. So when the current goes through the coil, the magnet goes up and hits the bell. Right? That's the doorbell thing. So same thing with light. So you have an electric field that's generated somehow, right? And then so you set up a pulse, like you just blow something up and you get an electric field because it's got charges in it. So if you blow something up, there's ions, right? They're going to have like some kind of charge. They move. That makes a magnetic field. And if you have a big enough explosion, you give off electromagnetic radiation. Because once you make a changing electric field, you automatically make a changing magnetic field that's normal to it. So you can't draw it. It's like in and out. Right. And it's out of phase. So I drew it wrong. So where this is changing the most, the magnetic is most. Good to get these marginally accurate. And it changes sign with the direction of the change. Right? So this is kind of an invisible magnetic field associated with the electric field. This is plain polarized, but we drew it. So it's the kind of light you would get from it's monochromatic because it's got only one wavelength, and it's plain polarized, and it's coherent, meaning that I'm only drawing one, and it's implied that all of them are the same. All right, so coherent is sunlight because the light, after it travels, all the incoherent radiation would destroy itself. If it's out of phase, it would burn out if it travels far enough, right? So there's a distance over which, like a light bulb, so you have a normal incandescent light bulb, there's a distance over which it'll go to zero. That's called the coherence length. And so there's some length, like lambda coherence, where the light will disappear. And it's a different light bulb. I think for a light bulb, that's like 100 whatever feet or something for a normal light bulb. Right. For a synchrotron X-ray source, the coherence length is on the order of like it's like 500 meters or something. For a laser, it's really far. So lasers, because the event that caused the electric field to change was all at the same time. So in other words, in a light bulb, it's just random. You're like exciting electrons are flying off, like stuff is just flying off all the time. It's like just a random explosion. With a laser, you're putting in like you're putting in electricity that's oscillating at a certain frequency. Everything's like perfect. It's in a perfect crystal. right? And it's everything coming off is so it's totally coherent. That's why the laser can go all the way across the room and the cat follows it. Right? Whereas a flashlight, you couldn't care less. Right? So basically, this coherence length is important if you want to do measurements in sync. So you have a lab source X-ray would be like you have a filament, you have a big voltage gap, like kilovolts. The electrons fly off, they hit the metal. So then you have an electric field that stops, like the charge just stops. It hits a wall and it stops. That gives off what's called Bremsstrahlung radiation, which is like white radiation. Brem is a break in German. So Bremsstrahlung is radiation, so it's breaking radiation. It just gives off this radiation that's just like breaking radiation is just going to have like a Gaussian peak or something in energy. That's versus wavelength. You just have this blob kind of white light coming off. Synchrotron, you put some kind of charged particles. It can be like electrons, positrons, so antimatter or matter. So they usually use antimatter because if it leaks out, antimatter annihilates, whereas electrons don't. So antimatter is actually better than matter for synchrotrons because it's safer. So basically, they somehow make antimatter. They put it into a big ring. It's like a half mile across. So people, they have in Switzerland, they have a foot race inside the ring. So they built a wooden synchrotron near Zurich, and then they have a foot race indoors inside the ring, So they shut it off when they do it, but basically they do that. Anyway, so it's a big thing. It's a big like indoor track almost. And then anyway, because they put that through wigglers and other kinds of things, but basically if you have a controlled change in the path of the particle, then you're going to get like good coherence length, monochromatic, and it's going to be polarized because there's a certain direction to this thing. The other way to get polarization is to reflect off a surface because the electric field has to be in the surface, right? When you reflect, that means when it reflects off, it has to be polarized. It's polarized in the plane. That's why if you put on like Polaroid sunglasses and they're polarized in the other way, like that way, then you lose the glare. Like Polaroid sunglasses, which are iodine molecule in polyvinyl alcohol. And somehow that mixture, if you extrude it right, makes a polarizer. The iodine is the source of the polarization. Anyway, so those are the things you need for light. You need monochromatic, you need coherent. These are all the positive things. And then you need to have plain polarized. Sometimes you need that, sometimes you don't. So anyway, that's kind of what's going on here with this picture. So we have monochromatic, coherent. We're only looking at like one wave kind of. And then you're saying like I'm taking like 1.54 angstrom X-rays, and then I'm going to hit something in here, and then it's going to come out at 1.54 at this angle theta. Right. So in order for that to happen at the angle theta, at this position in here, which is going to be your source, you have to have material at these spots where the two things match, right? The Moiré fringe lines. So you have to have something there that's going to be excited by the magnetic field, so electrons. So electrons are going to like shift up and down when the electric field hits them. Then that becomes an oscillator that's going to generate another electric field, just like when you put a rock in the water and it makes the waves go out. Right. So anyway, so you have to have stuff at those positions, but the position of those positions changes with the angle. So if you're at high angle, it's small, and if you're at large angle, it's big, and there's no limit to how big. So I can take 1.54 angstrom radiation, and I can measure microns with it, because there's no limit to the big size. So this is kind of small angle, big size, then big angle, small size. So that makes you, if you look in over here at this side at a detector, so you're far apart. Close end means big things, and far out means small things. Also, infinity is easy to reach here. You just go to 0. but there's a finite limit at the high end, which is your wavelength. It's half of the wavelength. Right? So if you can see, if these lines are by wavelength, when you go to the high end, you get to like half the wavelength. Right? So you end up with like lambda by 2. So you're gonna have your size scale D is going to be lambda by 2, and then it can get to be any size. So that sine of the angle by 2 amplifies it. And this can go to 0, so that can go to infinity. If you have a way to measure a 0 angle, which you don't. So basically, that becomes an instrumental problem. That's a technical problem.
Can't build it with the detector.
Well, your beam size becomes a problem too. Like you have a centimeter beam, or here a micron, 20 micron beam. You can't really measure bigger than a 20 micron, because basically it gets to be illogical, I guess. So anyway, so that's kind of the game of it, that you're playing. It's like to work with these fringe things, and you can see like, if this really is plane polarized, then the orientation of this thing matters too. So orientation is going to, if this is a 3D thing instead of 2D, then the orientation of it matters. Like you have to think about the orientation. So the orientation is going to be reflected, and then the structure is going to be reflected, but in this kind of weird way. Like you're probing, you have a size probe you're throwing in, the intensity is related to the amount of material. So you have the amount of material at that size. That's kind of the idea of it. And you can see that it's half the angle. So see these black lines are at half the angle that I tilted it. That's where the half the angle comes from. At some point you can see it, but the black line is at half the angle of the wave that's coming out. Right, so it's lambda by 2. Anyways, that's it. That's kind of what the whole thing is. So then you say like, the stuff that's on the black lines is floating around in space, just randomly oriented. So this is a 3D probe because the waves actually, so it's actually probing space in 3D. It's not doing it in 2D or 1D or whatever this is. Right? So it's like a 3D probe of space. So anyway, so your stuff, like whatever the thing is, it's kind of like that. And the spacing of these lines, you can just call like R. It's a vector. It's floating around in space. And so you can say like, there's your stuff, the things in it. It has stuff at the 2 points, so it's going to give a wave at that distance. Right. So if your stuff is like randomly floating around space, you either rotate the stuff or rotate space. You could rotate the R, put the R wherever you want, or you could move the stuff around. And when you do that, everything becomes Gaussian in the end. Like no matter what you started with, if you start at random points in it and then spin it around anyway, where you have the 2 ends of the thing land in the stuff, then eventually, so it could start at any point. So it's going to be like, there's going to be a center of mass, or it's going to be most likely that you have the 2 points, and then there's going to be points further out, but less and less likely because I mean, I'm not sure how to demonstrate that, but that's kind of how it would work. Like in other words, let's see, I guess you could demonstrate it kind of. So say you had like a triangle, center of mass is there. So if I start there and I go out a distance, R, like a small distance, and then I could move the thing. So I could start here, move out a small distance, start here, move out a small distance. So I'm going to add those all together. So I'm going to take this one and put it in the middle, and then take that one and put it in the middle. And take this one and put it in the middle. You can see the middle is going to have the most stuff. Like I start going around in circles, like how much stuff. So the middle is going to be the peak. So it's 0. And then as I go out, like when I get to the furthest point, that's going to have the least. And then at some point it'll go to 0. Right, so I'm going to have like, it'll be cut off, and then it's going to have like, at least it should go up and down. Right? I'm saying it's going to be a Gaussian for anything. So the center of the thing randomly rotated is going to be a Gaussian. That's the idea of it. So if that's true, if that's true, then basically that density of the stuff is going to be a Gaussian. And the way you can figure out that that would be like the moment of inertia for the object. That's kind of what this RG squared Gaussian decay. So this is a Gaussian function. It's a decay, it's negative, and it's R squared. So it's got no direction to it. So it's symmetric. And that's the lowest order that wouldn't add to 0. And then the weighting of that is the sigma, the standard deviation of that is going to be this RG squared thing. It's going to be the moment of inertia. And if you, so the way this works is that you need to, so you're measuring the amplitude of the thing. I mean, you're measuring the intensity, which is the amplitude squared, because the amplitude of the wave that comes out goes like plus and minus, right? But your intensity only goes plus. Like you can't measure a minus intensity or it'd be like a black hole, like suck up light. So that's not possible. So you can only really measure the square of the thing, and that's the intensity you measure, the square of the electric field vector. So anyway, what am I trying to say? Oh, so and the intensity you're measuring is in this angle or in like Q space. Q is the angle. So it's the angle kind of reduced by the sign thing, so you get the actual distance of that vector. So Q is like the vector that you're looking at. Right? So if you look at it inside a detector, so it says an R vector is a Q vector. This is called real space. This is called inverse space. So Q is inverse space, R is real space. So if you think about, so what's a Fourier transform? Okay, transform from time to frequency. So you say, if I have some kind of signal in time, so like a noise pattern, right? And then I want to know what's that thing in frequency domains. That means it's composed of like a bunch of sine waves. It's composed of that sine wave, and it's got this sine wave. So you can break this down into a series of sine waves. You could add up and you could create that noise pattern you have. Right? So it's possible to convert from a time domain to a frequency domain. But if you had, say you had a bell, right? And then that's going to ring at a single frequency, then that bell would look like this. Like it's going to have just one thing. Right. If I wanted to put that to frequency, it's only got like one wavelength to it, so it would have like a single tone to it. But bells have multiple tones, and also it decays with time, right? So it's not just that; it also has to have the opposite of it. So it's going to decay with time. It has to have some component that's opposite. So basically, the bell's going to have like a bunch of different tones to it. And it's going to have like overtones. You have frequency 1, frequency 2, like 3 orders, right? So you can, like on a guitar string, you can pick the points where it has overtones. I don't know if you've ever done that, but basically this, with the guitar stringing, it's got like the tone of the string and then all the overtones to it that are going to be at frequency 1, 2, 3, 4. So it's higher and higher pitch. So if you hold it up close to the neck of the guitar, it's like a really high pitched thing. Anyway, so there's also all other kinds of tones in it because it's got the body of the guitar. There's all kinds of things going on in it. So there's other frequencies involved in it. Right? If you look at it and just time and amplitude, it's like a noise pattern, but you can break it down into these basic frequencies that reflect like what it is. Okay, so in the case here, we're kind of measuring in this real space, or the structure is in real space. So it's got structural features, like say it's a crystal. So in real space, it's going to have like the bell, it's got a fixed frequency, or it could have, I mean, all the crystal planes, but basically one of the planes will give rise to one frequency, and this is space. This is like density, electron density for X-rays. And then you're measuring it in this frequency space, which is Q, like the wave vector. So it's inverse space. Frequency is 1/time for hertz. Right? This is time, seconds. Right? So this is Q and R, kind of the same thing. And then this thing's gonna, if it was that, it would end up with a spike. That's a diffraction pattern. Right? It's an amplitude squared, but it's going to be a spike to it. So here we have a Polymer coil. It's going to have a lot of noise pattern, right? And we're going to transform it, and it'll be this Guinier's law thing, and maybe a power law. We're only kind of interested in the Guinier's law. So those are related by what's called a Fourier transform. You take your signal, your amplitude of time, and you do this integral from time equals 0 to infinity. This E I omega is like sine omega t, 2 pi here too, and then minus I cos omega t. So this is the sine. It's breaking it into the sine wave. There's an imaginary part too. Basically, it's breaking into sine waves. So your amplitude at time t is composed of these sine waves. So you're weighting all the sine waves that gave rise to that signal, so the sine waves, by the amplitude. And you can transform that to the Fourier transform of it. It'd be like amplitude is a function of frequency. And here we're doing electron density as a function of space, becomes the amplitude as a function of Q. They transform. Same, it's not time, it's R here, and it's not frequency, it's Q. This is they're vectors, so it's a dot product. These are scalars, so it's a little bit different because these are vectors. So you can have orientation reflected in it. But it's the same kind of process. You're breaking apart a noise pattern into like a signal. So anyway, we want to do that transform with this Gaussian thing. So we got the Gaussian, somehow we created a thing that's a Gaussian. The Fourier transform of a Gaussian is a Gaussian. So Fourier transform has some rules to live by, but one of them is a Gaussian's a Gaussian. So you have a Gaussian distribution of the stuff that's going to transform into a Gaussian. And basically it's you replace the real space with the inverse space. And the RG flips up here so that it becomes unitless in the argument. And you get this third comes from that. So that's kind of how it would work out. So you can do the transform of that and get this. And this is Guinier's law. So that's one way to look at it. There's a bunch of ways to derive Guinier's law. But I think this is a useful one because it gives you a structural interpretation of what it means. So what it means is that the structure is a Gaussian. Okay. So Gaussian, there's some features about a Gaussian that's kind of useful to know about the limits of the Guinier's law. So Gaussian doesn't have a surface, it's a cloud. It goes to infinity. Right, so it's got a peak in the middle and it's just a cloud. It doesn't have any surface to it. So when you plot log I, log Q, and it's just that, that means you're looking kind of at a cloud. So that's true if you're looking at the thing like from far away, you can't see the surface exactly. You know there's something there. So you know the amount of the stuff, you know its electron density squared gives you that I naught thing. But you can't see like you can't see what it is. So you can't see what it is. It doesn't have a surface. It doesn't have like an internal structure. So Guinier's law says it's just this smeared out thing, right? And all the information about what it is, it's like out here, beyond Guinier's law, right? So that's generally this power law. So for this case, it's Q to the minus 2 means this thing's 2D inside. So once you zoom in, then it's 2D. That means that the density is the mass per the volume, and then the volume is the size cubed, and the mass is the size to the df. So the density is going to go with the df minus 3. And so it means within the thing, it's going to follow that density rule. So it could be two things, or many things could follow that density rule. One is a disk that's flying around, and the other is this random coil thing. And the other could be a straight thing with enough branches to make it, so some kind of stick tree could be two-dimensional. Or, so, yeah, so that's kind of it. There's like three things it could be. Or you could have a combination of squiggly and stick. So it could be non-Gaussian and sticky. So you could have like an expanded coil with some degree of stickiness to it, or branches on it. So it's four. There's like an infinite number. So within, if it's not one, which is a rod, or three, which is some kind of solid object, then in that region, there's a lot of things it could be. And so anyway, two is one of them. So this, you need this power law to say what it is. This Guinness law kind of gives you the density, and it can give you the rate of gyration, which is how when this thing, like it's related to the density also. Like the rate of gyration is kind of related to the density. Like a dense object, RH by RG is less than one, and then a floppy object is like, so basically RG is telling you kind of what it is in terms of density, like in terms of mass density, right? So anyway, that's kind of how this is going here. So what else is in here? This is the same thing. That's all the same thing. So, I mean, that's kind of a philosophical thing. And then I showed you before how to calculate rate gyration for a sphere. It gives you this 3/5 thing. Then you can do that same kind of integral approach to calculate it for anything, for any kind of solid object. Right? So you can get an exact function for rate of gyration. So it's nice for regular objects. You can get a direct relationship between what the structure is and kind of what the rate of gyration is. So it's a nice hard number that you can get. Even though, like I said, if you do a Guinness plot, it becomes a soft number. So if you kind of know what you're looking for, what the size is, it's a really useful number to have because you can directly relate it to the structure of the thing. It's like tobacco mosaic virus is like a rod or something. And then you can find the rod one pulse or some kind of cylinder. I guess I didn't put cylinder here. It's kind of weird. But anyway, cylinder one's like this 12. A and B are the same. So it's the radius squared by 4, and then the length squared by 12 for a rod, right? For tobacco mosaic virus. And you can get those dimensions from its X-ray scattering of it. That's what that was a big thing in the 1950s, like when they first kind of figured that out. And this, the paper from the guy from Cornell, he did that for all kinds of weird proteins, like all the different protein shapes, you know. So anyway, so the next thing is like a polymer chain. So it's basically going to be like the same summation, double sum that we did for the rate of gyration, you do for a Gaussian density distribution, or you do for a polymer chain density distribution following Gaussian equation, and then they can calculate what the scattering function for polymer coil is. Debye did that during World War II when he was at Cornell. It was classified because it was for the natural rubber project. So it was classified and wasn't released until 1956 or something. But the scattering pattern, which is totally useless, like to make a bomb or anything. But it's kind of funny. He was working because of the Japanese controlled the Malaysian source of rubber, you know, so the US needed rubber to make airplane tires and stuff, and tank treads or whatever we needed. So they thought that anything that had to do with, they had kind of a Manhattan project to make synthetic rubber. The Canadians and the US did it. They succeeded, you know, they made synthetic rubber, and then but this scattering function was, they were being paid by that, you know, so it's like part of the war effort. Anyway, so I'll go through that next time, like that, how to get the Debye function thing. So, all right. Hopefully this thing recorded now.